Hey, Algebra 2. Today, lesson 30, buying a car. We're still dealing a lot with interest rates and compounding interest, etc. So last lesson, we talked about, what was the title? Mathematics Behind Structured Savings Plan. Today, buying a car, and it's just a lot of fun, these last few lessons. All right, our opening exercise, write a sum to represent the future amount of structured savings plan, the annuity, if you deposited $250 into an account each month for 5 years that pays 3.6% interest per year compounded monthly. Find the future amount of your plan at the end of 5 years. So this is what we did last lesson. Really, we have $250. We deposited 3.6%. That would be 3.6 over 12, which is 0.3. 0.003 in decimals, 0.3 in percentages. All right, so I just needed to do that to get this number right here. Raised to the 59. Okay, 5 years is 60 months. Cool. So we would do this how many times? Many, many, many times. Just giving you an idea. Plus dot 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 plus 250. Okay, that's our sequence of numbers. Yeah, we're not going to calculate that. So we simplify it using the equation that we developed last lesson, raised to the 60 minus 1 over 0.003. Okay, so this right here is the equation that we developed last lesson. If we crunch all those numbers, that gives me $16,407.90, right? So the amount in the account after 5 years would be $16,407.90. Awesome. Now let's get into the lesson, see where we apply this knowledge, apply these equations to buying a car. So I don't have my awesome stylus today, so we're struggling along with my backup stylus, so I apologize in advance. But it's all right. You guys don't seem to mind. Or I'm not there for you to complain. So Jack wanted to buy a $9,000 two-door sports coupe, but could not pay the full price of the car all at once. He asked the car dealer if she could give him a loan where he paid a monthly payment. So she told him she could give him a loan for the price of the car at the annual interest rate of 3.6% compounded monthly for 60 months, which is 5 years. The problems below exhibit how Jack's car dealer used the information above to figure out how much his monthly payment of R dollars should be. First, the car dealer imagined how much she would have in an account if she deposited $9,000 into the account and left it there for 60 months at an annual interest rate of 3.6 compounded monthly. Use the compound interest formula, F equals P times 1 plus I to the N, to calculate how much she would have in that account after 5 years. This is the amount she would have in the account after 5 years if Jack gave her $9,000 for the car and she immediately deposited it. Okay, a little backstory here. Many people, almost everybody that you know, take out a loan to purchase a car and then repay the loan on a monthly basis. We're going to figure out how banks determine the monthly payment for a loan in today's class. It's hard to save up enough money to purchase a car, especially a brand new car. They're quite expensive. I saved up money to buy my first used car when I was 16, and now I generally save up to buy new cars or even new used cars. But loans can be expensive. You end up spending a lot more money on the car than the sticker price, and that's what we're going to sort of walk through today. So when deciding to get a car loan, there are many things to consider. What do we know that goes into getting a loan for a vehicle? If you have a down payment, would be one thing you'd look at and use as part of the calculation. A down payment. What kind of money do you have? to pay a monthly payment. If you have, you need some extra money in your pocket each month to make your monthly payment. What the interest rates on the loans are. These are all things that you need to consider when buying a car. The number of years of the loan. We're talking about 5 years, which is 60 months right now. Number of years of loan. I think we understand this. Down payment is how much money you have in your pocket to sort of pay down the total amount of the loan. Say you're buying a car for $9,000, you have $4,000 in your pocket, so you give them $4,000, which means you only have to take out a $5,000 loan. Pretty awesome. Monthly payment, it's what you pay towards the loan each month. Say $250 a month to try to pay down what your loan is. Interest rates on the loan, so the bank charges you an interest rate to take money out of the bank to pay for a car. That means that you're paying the bank more than the amount of money that you took out. Say if you took out $5,000 to pay for a car, they're going to charge you interest for giving you that money. So you're going to pay them more than $5,000 back. And then the number of years on the loan. How much time do you have to pay that loan back? Cool? All right, let's get back to the problem. So here we're using the equation. $9,000 is what the loan is for. 1 plus 0.003 to the 60. Okay, 60 months. P is the principal of the loan. I is the interest rate. It's the compound interest formula that we learned a few lessons ago. If I go ahead and crunch those numbers, I would get $10,772.05. So at the end of 60 months, that is how much money is in her account. Not too bad, not too awesome, but not too bad. Okay, let's move on. Next, she figured out how much would be in the account after 5 years if she took each of Jack's payments of our dollars and deposited it into a bank that earned 3.6% per year compounded monthly. Write a sum to represent the future amount of money that would be in the annuity after 5 years in terms of R, and use the sum of a geometric series formula to rewrite that sum as an algebraic expression. This is what we practiced doing before, back in lesson 29. So the future amount of money in the account after 5 years can be represented as follows. Okay, remember? And we could keep going, but we don't want to do that because that's a lot of work, especially when it's 60 months. Right? So applying the sum of a geometric series formula, we're going to get S sub n equals A 1 minus r to the n over 1 minus r. Using the values that we have, I have A equals big R. The rate is 1.003 and n equals 60 days, or 60 months, I'm so sorry. We get S sub n equals R, 1 minus 1.003 to the n over 1 minus 1.003. And you remember we messed with this equation last lesson and simplified it to look like this. Yep, which actually is what I wrote right there. Okay, I copied that from the last lesson. So that is our sum as an algebraic expression. Cool? Alright, so we just re-derived the future amount of an annuity formula, right? Alright. So the car dealer then reasoned that to be fair to her and Jack, the two final amounts in both accounts should be the same. That is, she should have the same amount in each account at the end of 60 months, either way. Write an equation in the variable r that represents this equality. So what we did in the beginning, which was the 9,000, 1.003 to the 60 should be equal to this equation, 1.003 to the 60 minus 1 over 0.003. So those should be equal, which means we can solve for r, right? Part D, which is on the next slide, but you see it in front of you, she then solved her equation to get the amount r that Jack would have to pay monthly. Solve the equation in part C to find out how much Jack needed to pay each month. Alright, so I am just going to take this amount, divide both sides. So I'm going to have 0.003 over to the 60 minus 1 times 9,000 times 1.003 to the 60. That equals r. Get out my handy dandy calculator, start crunching some numbers, and r is approximately 164.13. Those are Jack's monthly payments for 60 months. Fun. Oh, we already did this. Last slide. Cool. So, this $164.13 means that that's what Jack is going to have to pay every month to repay his loan for 60 months. Okay, it's a lot of money. So for example, if Jack decides not to buy the car and instead deposits $164.13 a month into a new account, earning 3.6% interest compounded monthly, how much does he have at the end of 60 months? So 60 months at 3.6% compounded monthly. If he just deposits that kind of money for 60 months, he has $10,772.05. The final amount of the annuity that the car dealer calculated in part A or B. Okay, so that's really what his car is costing him. An extra $1,772. Sort of stinky, right? All right. Okay, what we just developed through those exercises is called the present value of an annuity. It's Annuity formula, which is A sub P R 1 minus 1 plus I to the negative n over I. I could show you how we redistributed all of the variables and did some algebra, actually FOILed something to come up with this formula, but it's okay. Like, this is what we're going to write down. This is our present value of an annuity formula. In the exercises, we took two equations and solved for R. That's what we did in the example. But it's much more common in finance to solve for A sub P. So that's what we did here. So this formula is much more useful in finance. So when a bank or a car dealer makes a loan that is to be repaid with recurring payments R, these right here are our recurring payments, then the payments form an annuity whose present value A sub P. So we have annuity whose present value A sub P is the amount of the loan. So I can say amount of the loan. So we can use this formula to find the payment amount R given the size of the loan A sub P. Amount of loan, size of loan, recurring payments. Or we can find the size of loan A sub P if we know the size of the payments R. So it's a very useful formula. We can find this if we're given that, or we can find this, this if we're given that. Okay, it goes back and forth. All right, let's try an exercise. A college student wants to buy a car and can afford to pay $200 per month. If she plans to take out a loan at 6% interest per year with a recurring payment of $200 per month for 4 years, what price car can she buy? So let's get our formula out. I've got A sub P equals R. 1 minus 1 plus I to the negative n over I. Let's go ahead and substitute and solve. Okay, the recurring payment is $200. I have 1 minus 1 plus, and I have for I, um, 6% interest per year would be 0.5. That's in percentages, so let's change that to decimals. To the negative 40, are all these making sense? Over 0.005. If I crunch all those numbers, I get 8,516 and 6 cents. So she can afford to take out an $8,516 loan. So this is the size of loan she can afford. If she has no money for a down payment, she can afford a car that's about $8,500. Okay, if she had a down payment, it'd be nice, but if she doesn't, then that's about as much as she can buy a car for, right? Last minute addition to the video. I've come back to change something. This right here is incorrect. Oh, goodness. It should be 48. Okay, we're at 4 years. 12 times 4 is 48. So everything is in months here. This is in months. This is in months. That's why I did that. This is in months. So everything's in months. So this should be to the 48th. And everything else is correct. I just had a typo, handwriting typo. Thanks. All right, let's do a mathematical modeling exercise. All right, in the problem set of lesson 29, you research the price. Oh, actually, we didn't do that. I didn't assign this problem to you, but that's okay. In this exercise, we determine how much a car payment would be for that price for different loan options. So let's just all pick the same one. Let's pick the 2007 two-door small coupe. It's for $7,500. So when you buy a car, you must pay sales tax and licensing and other fees. Assume that sales tax is 6% of the selling price, which you have to pay when you buy something, and estimated license title fees are 2% of the selling price. If you put $1,000 down in the payment for your car, how much money do you need to borrow to pay for the car and taxes and other fees? All right, so the car is $7,500 plus sales tax plus fees minus how much money you put down. Crunch some numbers. Give me 1 second. I'm going to push pause and crunch numbers. So that's how much money she needs to borrow. Okay? I did the price of the car plus sales tax plus fees minus her down payment, and I got $7,100. Using the loan amount you computed above, calculate the monthly payment for different loan options shown below. So we're going to calculate this 3 times. All right, what I've done is calculated the first loan, step you through it. I set up the equation, $7,100, what is my recurring payment, all of the interest rate stuff. I got this value right here, 2%. So 2 divided by 12 is 0.167%. So I need to change it into a decimal and do 1 plus the interest rate. So 1 minus 1 plus the interest rate to the negative n over the interest rate. So take the $7,100, divide by this monstrosity, and I got $203.37. Yep. So that is what the monthly payment is. So I'm going to go ahead and try the second loan. R1 minus 1.0025 to the negative 48 over 0.0025. Let me crunch this. I'll be right back. Here I got $157.15. One more. Be right back. All right, this last one. I got $133.998776. To me, that rounds to $134. The answer in the book is $133.99. So we have some rounding issues for that one, but that's okay. That's why I gave you both answers. Cool? All right, so that's the using the loan amount you computed above, $7,100. Calculate the monthly payment for the different loan options shown below. Like, which one would you want? Would you like to pay a lot of money for a smaller amount of time, less money for a larger amount of time, or even less money for 5 whole years? So which plan, if any, keeps the monthly payments under $175? Of the plans under $175 per month, why might you choose a plan with fewer months even though it costs more per month? Well, loan 2 and 3 are both less than $175. And it's your choice what you would do, but when the monthly payments are close, like loan 2 and 3, and fewer payments you make with loan 2 means you pay less overall for that loan. Like, this is for a shorter period of time. And you don't want to pay for your car forever. You'd like to buy some new shoes or go on vacation or something else with the money that you would be spending on your car. So personally, I like to pay cash for a car, but if you can't do that, try to maximize your down payment and then pick the shortest loan you can with the amount of money you have. Oh, and that's it. I added another slide again. Good work today.